So we will be talking about mean value theorem, Rolle's theorem. So Rolle's theorem, you see the spelling is not R-O-L-L, it's a Rolle kind of a thing, Rolle's theorem, and the mean value theorem. So what he tries to say is, if for example you have a function and the function is coming like that, this is the function value, that means f of x, this is f of x. So for some good reason it can be like this, or it can be maybe this way, some part. I mean, there can be much more. I am only talking about some part of the graph we have taken. It can be this or that. Let's say this is g of x, and we take two values of x equal to a, and we put this, we see whatever is this, and that is nothing but this is what we call as f of a, because we substituted x equal to a. This value is called f of a. And let us suppose you got exactly the same value of f of a for x equal to b. Understood, right? So you got exactly another value, same value for x equal to b. Here also it will be like that only. This is x equal to a, and this is g of a, and this is x equal to b. So if it's something like, if you are going up the hill, okay, if you know that you are going up the hill, obviously you will reach a peak and then you will go down the hill other side, or you are coming down the valley. It can't be like abyss. After some time it will become flat and then you will maybe going up, right? So if you are seeing that both these points are the same height above the sea level, or whatever from the ground, same height, that is exactly what we are doing. So what Rolle's theorem says, the first one is the Rolle's theorem. What Rolle's theorem says is that if the function is continuous meaning, let us now consider that it is having no break, okay, no discontinuity, where between a and b. That's what they'll state as in the interval a, b. Whenever they use square bracket, that means x equal to a, x equal to b, both are included. This interval we call included interval. Okay. When we say a, b, that means these are not included. A and b not included. That's a notation. Okay. Because we have to write it in the solutions, right? So we have to say that definitely for all the verify Rolle's theorem and all, verify mean value theorem, he says when he is stating the theorem, he says if f of x is continuous. When we are solving, we have to write it f of x is continuous in whatever is that interval, okay, and the next one is it is continuous and differentiable. Differentiable meaning when you do the first differentiation, you should get some value. That's what differentiable meaning. If you don't get anything, that means you are getting some infinity or something like that when you try to differentiate, then that particular thing is called non-differentiable. Okay. So in this case, first example, it can be f of x or it can be g of x. So there is no break between a and b. That is condition number 1. No break and differentiable. And also if f of a equal to f of b. F of a equal to f of b. F of b is nothing but same f of a value, right? Okay. Then the statement says that if f of a equal to f of b, then we will have, or there exists, okay, both mean same. Okay. We will have a point x equal to c in interval AB. That means between A and B, x value that x equal to C, right? Such that you will have this as either a peak or a minimum point or a maximum point. So we will say that such that you will have equal to such that f dash c equal to 0. So the differentiation at that point C will be 0. This is what the Rolle's theorem. Okay, so let us take the mean value theorem also here itself. Mean value theorem, it is not 0, everything else is same, but f dash b is equal to f of b minus f of a divided by b minus a. But obviously, right, here it is continuous and differentiable, then there exists a value sum c between a and b such that f of b minus f of a divided by b minus a, you will get f dash c. This is in which case if f of b is not equal to f of a, isn't it? F of b is not equal to f of a. If it's both are same, then MVT is nothing but the Rolle's theorem. Okay, so just remember this. When we are doing the questions, we will have. Hello? You can hear me, right? I just heard some sound, that's why I was just wondering if from my mic. Okay, so they won't ask you to prove this theorem or whatever, straight away questions. So this exercise 5.8. Verify Rolle's theorem for the function f of x equal to x squared plus 2x minus h, and x belongs to the interval is -4, 2. So we have to state f of x is continuous in -4 to because it is a polynomial function. All polynomial functions will exist without break if they are continuous. Okay. Also, f of x is differentiable in, just have to put curved brackets, -4, 2. These two statements you have to write. Okay. Then you write f of a. In our case, a equal to -4, b is equal to 2. F of a equal to f of -4, that's equal to -4 whole square plus 2 into -4 minus h, that's equal to 16 minus h minus h, which is equal to 0. Correct? So f of b equal to f of 2, that's equal to 4 plus 2 into 2, 4 minus 8. This is also equal to 0. Any questions? So therefore f of a equal to f of b. So now, in order to prove that the Rolle's theorem is verified, or in order to show Rolle's theorem is verified, we have to do f dash x. F dash x is how much? So f dash x equal to, so you are writing x square, right? That is 2x plus 2. I differentiated this. X square differentiation is 2x. 2x differentiation is 2. 2x plus 2. Okay. So we are equating this 2x plus 2 to 0. Then f dash c, that is nothing but 2c plus 2. I mean, I substituted c instead of x. Why? That's what Rolle's theorem stated, right? So you need to have f dash c. Where is that written? See here, f dash c equal to 0. I wrote it here, right? So that's why we need to be showing f dash c to be 0 there. So this is f dash c. So equating that to 0, we get 2c plus 2 equal to 0, which implies 2c equal to minus 2, c is equal to minus 1. Now if you look at the number line, he has given minus 4 and 2. These are the intervals he has given. Right, that's the interval. He said minus 4 comma 2. We got c equal to minus 1. Where falling? It must be falling somewhere here. Right? So this is A, this is B, this is C. So since C lies between A and B, Rolle's theorem is verified. That's it. So you may get this for 3 marks, not more than that. So now the questions, whatever is given, examine if Rolle's theorem is applicable to any of the following functions. Can you say something about the converse of Rolle's theorem from these examples? First thing is, you won't probably get the converse and all the things in the boards. They have not given. Okay. So even third question. The first question is a good question. Then you will have fourth question and fifth question in this. Okay. So he's asking, like, even the sixth question, if you see, examine the applicability of Min Value Theorem for all 3 functions given in the above exercise 2. Okay. Exercise 2 meaning his question number 2. Okay, that's what he means, sixth question. So I'll first explain that what is given in the second one. F of x is equal to, he has given with the square brackets. Okay, so for square brackets, what is the kind of a function we have? I'll tell you that. Then third question is the straight question. Third one is, second main, third one. Okay, so what is this square bracket x? Square bracket x question is, this is called greatest integer function. I will draw the graph. In fact, you can actually, you have textbook with you, right, in front of you. Correct? So I'll tell you the page number. You can directly go to that page. Okay. Go to page number 155. So there, you see the graph figure 5.8. Okay, so that 5.8 is what I'll be actually drawing here. That's what the greatest integer function means. So it looks, for example, you have 0, minus 1, 1, 2, 3, 4. So between 0 and 1, you see there is some thick filling like this, and then you have, and then like that. Got it, right? From here, thick filling like this, you have like that, and like that. Thick filling like this. So what it means is the graph. I'll explain the graph first. Okay. So wherever you have straight line, this line, there no break. There is no break basically. But at x equal to 2, right? There is a hollow here and there is a thick here. This value is 1 and this value is 2. It is having two values. But x equal to 2, right? Actually this one, whatever is the filled one, right? That's what it means. F of x is equal to 2. But when we are coming at x equal to 1, f of x equal to 1. If I take x equal to 1.5, that means anywhere here, 1.5 also, f of x is equal to 1 only. Understood, right? So for anything B2, between 1 and 2, the value is 1. Between 2 and 3, the value is 2. But then there is a break or jump. There is no break, but there is a jump at all these points. Jump from 1 to 2. So this greatest integer function is having a jump. So there are two types of discontinuities. One is called the break discontinuity or a jump discontinuity. So there is a discontinuity. As per Rolle's theorem, the Rolle's theorem is valid only for continuous functions. So both 1 and 2, got it right? They are not functions, not continuous functions. Therefore, Rolle's theorem is not applicable. So obviously this may come as a 1 mark question, it won't come as a 3 marks question. Okay. Now we'll go to the second main, third one. So the third question. So here x square minus 1, f of x equal to x square minus 1, a is equal to 1, b equal to 2. So f of a, it is a continuous function because it is a polynomial. Continuous function, and differentiable. You can say differentiable. Every continuous function is differentiable. So f of a equal to f of 1 equal to 1 minus 1 equal to 0, a equal to 1, f of b equal to 4 minus, that's equal to 3. Is f of a b? No, right? F of a is not equal to f of b. Therefore, Rolle's theorem can't be applied. Understood, right? That's how we'll write it. So this is also not for 3 marks because you're just testing the conditions. See, the question was, examine if Rolle's theorem is applicable to any of the following functions. Can you say something about the converse of the Rolle's theorem from this example? What we mean by converse of Rolle's theorem? So we moved forward in the Rolle's theorem saying that if something is continuous and differentiable, and then there exists a value of c such that f dash c equal to 0. The converse of the Rolle's theorem is, if f of f dash c is not equal to 0, f of a equal to f of b, okay, then can we say that this function is not differentiable, not continuous? That's, see, if you look for the answers for this exercise 5.8, right, there are no answers. Okay, so it's only the verification thing only. That's why I'm explaining this. Okay, and therefore the converse also. Okay, if something f dash is equal to 0, so you got 2x and anywhere it will be 0, then obviously the converse must exist. That means if f dash is equal to 0, then you have f of a equal to f of b. The function is continuous and differentiable, but it is not possible for any of these things. All the three, f dash c is not equal to 0. Got it right? That the converse also doesn't exist or not valid. Question number 3. F is to minus 5 is to 5. That means we are talking about two values between minus 5 and 5. That is one f of x. F of x is a differentiable function. F is differentiable. He stated that. And f dash x does not vanish anywhere. So he is saying does not vanish, meaning it is f dash x does not vanish. So these are the two things here. Prove that f of minus 5 is not equal to f of 5. Okay. So first one he said, the second one is does not vanish. Does not vanish means it's a finite value. So f can be 0, can be 0. Okay. He doesn't say that it is a Rolle's theorem applicable. So we say f dash x can be 0. For what value it can be 0. So that's why we go with a contradictory here, contradictory proof. We assume that f of minus 5 equal to f of 5. F of 5 equal to f of minus 5. And since f dash x does not vanish, f dash x does not vanish, okay, then there must be either a maximum, or minimum. What I mean is, so you may have some function which is going like that or going like this. It can be this way or it can be that way. That is the only case you can have maximum value or minimum value. Okay, but then he says it does not vanish. Does not vanish meaning it is definitely you will have a function which is constant, like that, and then becomes 0. Okay. So how we are proving here? We are just going ahead and saying we assume that f of minus 5 equal to f of 5. Okay. So as per the Rolle's theorem, if f of minus 5 equal to f of 5, then you may have something like f dash c that's equal to 0. This is the Rolle's theorem. The other one is mean value theorem. What does mean value theorem say? Mean value theorem says f of b minus f of a divided by b minus a. So if b minus a, in this case, b is 5, a is minus 5, so b minus a equal to 10 you will get. So some difference, f of b minus this one, this particular thing exists, and hence you cannot have a f of minus 5 equal to The same reason. I'll explain this one more time. Go to the question what we did, x squared minus 1. We did the x squared minus 1 here. We have a equal to 1, b equal to 2. If you don't have f of a equal to f of b, right, f of a is not equal to f of b. So Rolle's theorem cannot be applied. In the same way, we are going ahead here and said, we assume f of minus 5 equal to f of 5. Then Rolle's theorem can be applicable. Whereas f dash x does not vanish, he said, okay, but he didn't say it's equal to 0. Remember here, he didn't say it's a 0. And therefore, but we need f of f dash e should be 0. But he said does not vanish and does not become 0. And therefore, f of minus 5 is not equal to f of 5. Alright, fourth question. This exercise is abstract. It will be like this only. That's why do not depend as such for marks. Okay. Fourth question. Verify mean value theorem if f of x equal to x squared minus 4x minus 3. What is the mean value theorem? Says f dash c should be equal to f of b minus f of a divided by b minus a. So a is how much? A is 1 is equal to 4. So get f of b minus a. F dash c equal to f of b is equal to 4 squared, is 6 minus 16 minus 3. This is f of b minus f of a will be 1 minus 4 minus 3. Okay, 1 minus 4 minus 3 divided b minus a. So b minus a is 4 minus 1. So you got 16 cancel, minus 3. And here you will have minus 7 plus 1, which is minus 6. So plus divided by 3. So you will have 3 divided by 3. That's equal to 1. So we have dash e equal to 1. How? By applying this theorem. But actually when you differentiate f dash x, by differentiation you get 2x minus 4. So now you equate this 2x minus 4 equal to 1. So 2x equal to 5. That implies x equal to 5 by 2. X is nothing but, he says f dash c, right? So this is nothing, is equal to 5 by 2. Is 5 by 2 belong to the interval 1 and 4? Yes, right? It is yes, because 2.5. 2.5 lies between 1 and 4. Therefore, mean value theorem is verified. Got it? So, try the, I think I'll do next question itself. Fifth question, right? So, fifth question. You practice learning each question. You practice at home. So, fifth question. F of x is x cube minus 5x squared. X cube minus 5x squared minus 3x. So, a is 1 and b is 3. So, we have to write f of x is continuous in 1, 3 because it's a polynomial. It is a polynomial function. It is differentiable curve bracket 1, 3. Then we have to say we can find f dash x. We can find f dash x, that's equal to 3x squared minus 10x minus 3. We'll make this as f dash c. 3c squared minus 10c minus 3. So we should get this value. We have to equate this to whatever c value you find out like last time. It should come between 1 and 3. Okay. So now let us do the f of a. F of f of 1 equal to 1 minus 5 minus 3. That's equal to minus 8 plus 1 minus f of 3 equal to 3 cube is 27 minus 9 5s are 45 minus 3 3s are 9. So 45 9 54. So you will get minus. So f of 3 minus f of 1 divided by 3 minus 1 equal to minus 27 minus of minus 7 divided by 2. That's equal to minus 10 you will get. You will get minus 20. Minus 20 divided by 2 is minus 10. So we equate this to this. So 3c squared minus 10c minus 3 equal to minus 10. So you get 3c squared minus 10c plus 7 when 10 comes this way equal to 0. So quadratic equation, by simply factorizing you will do this. Okay, because 3 7s are 1, right? So factorize 3c squared minus 3c minus 7c plus 7 equals 0. So 3c c minus 1 minus 7 c minus 1 equal to 0. 3c minus 7 equal to 0, c minus 1 equal to 0, c equal to 7 by 3 or c is equal to 1. What was our interval? Interval was 1 and 3. So interval is 1 and 3. See, it should be between. So c equal to, that is not a valid value. It is invalid. Whereas this one, c equal to 7 by 3 is between them. Because 3 2s are 6, 2 1 by 3. 2 1 by 3 lies between them. Therefore, mean value theorem is verified. So it should, because of this, MVT verified. So the sixth one is not required anyway, because I told, right, the functions are not continuous. For 2 1 and 2 2 it is no use. And then 2 3, that x square minus 1 and 2. So that you can do it. That's easy. We can, if you want, I think we can complete it, but we have time. So that one is only one part I will do. Sixth one, that's a 2 3. So f of x equal to x squared minus 1. So f dash x equal to 3x. So f dash c equal to 2c. We get f of a is, interval is 1 comma 2. 1 comma 2. So f of 1 is nothing. 1 minus 1 is 0. F of b, that is 2 squared minus 1, which is 3. So as per this, f of b minus f of a divided by b minus a equal to 3 minus 0 divided by 2 minus 1, which is equal to 3. So equate this. 2c equal to 3. Therefore c is equal to 3 by 2. So which is 1.5. So 1.5 lies in interval 2 1 2. Therefore, MVT is verified. Okay, so